So we'll move forward. Actually, as we move forward, Andrea, did you want a syllabus? Or did you look it up online? I've got copies. So general highlights. You guys have, what is this? Probably your at least fourth semester of chemistry. I figure the syllabus is fairly standard. And no one has any particularly large questions. But some of the highlights off of it. This actually came back as a comment from feedback. Apparently some student realized at the end of the semester that I did not emphasize enough how much time it takes to study. And it was odd because the hour choice they used was exactly what was in my syllabus. So we'll point it out again. You're looking at a minimum of 12 hours per week outside of class, outside of lab, to actually study and do well for this class. Okay, so be aware of that. It does take time to go through and pick these things up and do well. Okay? That said, you can spend a good portion of that 12 hours probably with me. I hold pretty extensive office hours. They're held up on the second floor of the library. It's library 228, so it's the Science Tutoring Center. So the intent is to actually draw you into the tutoring center so you can realize I'm not the only one that can help you. Chandler Gilbert is one of the best community colleges, as far as I can tell, at least within my experience, for the tutoring center features. Okay? We have very capable tutors even for organic chemistry. Okay? So please take advantage of that. I'm in there for scheduled 6 hours, and I'll probably be in there closer to 8 to 10 hours per week. Okay? So please take advantage of that time, get that help. Yes?
Do you know if Laura Tracy's going to be at this campus more than she was last semester?
I don't know that. She will probably spend most of her time at the other campus because I think they're more understaffed there. Fridays, I'm pretty sure she's here because the other campus is closed. So there you go. Laura Tracy, the head, I don't think she's the head tutor is the best way to call her, but she's got a higher title than tutor. She's really good with organic chemistry. She can help out when she's around. Okay. Textbook, officially, we're going to use, sorry, was that close enough of an answer for office hours? Okay. Textbook, officially, we're using the Smith 3rd edition. There is currently a 4th edition out there. It's also roughly 100 times as expensive. I'm pretty sure the copy of the textbook that I've got, the 3rd edition, I bought for $20 with shipping. And I think the shipping was $15. So you can get it really, really cheap. That's what we'll be using. It turns out that there is actually sections of that or sub this semester that aren't covered in that textbook. So I will end up writing my own for those sections, which does show up in the syllabus. Jennifer? Yes. With that, one of the big reasons why we can get rid of using the 4th edition textbook is that we'll do an online homework system, so we don't have to say, oh, it's this question in this textbook. Okay? Yes, there is an online homework system. If you read through the syllabus, I'm very lenient on how that goes through and gets graded. Okay? I don't have the exact breakdown memorized. But it's something like if you complete 90% of the homework correct, you get 100 points out of 100 possible. If you complete 80% of the homework correct, you get 90 points out of 100. Okay? So it's designed in such a way that if there are errors when entering things into the online system, that those errors are fixed and accounted for. We don't have to stress about, oh my gosh, this one problem destroyed my grade, now I'm failing. That one question probably does absolutely nothing to your grade. Okay? So look over those breakdowns. Make sure you kind of understand how that's set up. Its design and intent is to get you to practice, and that's about it. Okay? I should have the first homework up soon. I meant to get that up earlier, but I have to go through and actually pick all the questions. Another big thing that's kind of non-standard among syllabi would be the resurrection final. So we've got 3 normal exams throughout the semester. We will do, if you have an excused absence, you can do an early exam. Prefer to get it done before instead of after, but it's usually within 24 hours of the actual exam time. Pretty lenient on trying to get you in and actually take that test. Okay. That said, there's an extra little kind of bonus to that. we've got the resurrection final. So we will be using the ACS standardized exam for the final. If your percentage on that exam, the normalized percentage, is higher than any of your other exams, that will replace one of your other exam scores. Okay? The normalized percentage was something we actually incorporated last semester, and that actually worked out pretty well. Okay? How many of you that haven't had chemistry with me are aware of the ACS exam? What's the average on it? You know? Average percent-wise on the ACS exam, just to give you an idea of the difficulty?
50.
About 50%. Okay, that's the average. So that's why we normalize those. Okay, so the average on my exams tends to fall within the 65 range. Okay, so what will end up happening is we'll scale the ACS exam up to a 70%, and then that percentile will be what potentially replaces one of your other exams. Okay. The reason that we're sticking with the ACS exam, even though it is so ridiculously difficult, is that it gives you some way to actually compare to other locales. So if you wanted to apply to some academic institution, you now have a standardized way to say, hey, I scored in the 90th percentile on the ACS exam. Okay? Now that goes through and says this class was worth it for you. Okay? This class was valid. It wasn't just some flyby class that you got an easy A in. Okay? So it lends some weight to your grades. So it's one of the things that's nice about it, even though it can be very, very stressful. Okay? Last thing, very not standard, is extra credit. Okay? I offer extra credit from day one. Okay? What that extra credit is that you send me an email pretty much confirming the fact that you've actually done some work. Okay? That you've been working that week for the class. The idea behind this is that you just send me a quick email about what you learned theoretically in organic chemistry that week and some kind of general context behind that. One of the other things that I want to see within that as well, which shows up on this board but not on that one, is how much time you spent studying the material since the last dialogue, okay? Which we may change to that week as opposed to the last dialogue. Once you've submitted 12 of these throughout the semester, anybody that actually read the syllabus carefully, was it 12? Or is it 10? I don't know. I don't know what it was. So if you complete 12 out of the whole semester, was it 12?
Yes.
Okay. Then you get an automatic 2% boost to your grade. This is strictly 100% extra credit. I've had plenty of faculty go through, oh yeah, I offer extra credit. Okay, when do you put the points in? Well, before I sign the grades. That's not extra credit. Okay? That's a penalty if you don't do it. Okay? So what I'll go through and do is actually assign grades at the end of the semester, decide where the cutoffs will be, and then what I go through and do is go back and highlight anybody within 2% of that grade bump, and I go back to my email and see, did you submit those 12 submissions? If you hit that 12, no questions asked, you're bumped up. If it's not there, I don't bump you up. Okay? You get the grade that you had. Okay? So this really only affects the borderline grades or borderline people, and at least in my opinion, having lived on the borderline for most of my life as far as grades, if you're one of those students, you probably know, and this is a very good policy. Okay? So go through and start working on getting these submitted. It's not that hard. I'm not looking for massive paragraphs. I've seen dialogues as short as 2 sentences that go through and explain just enough to prove that you actually read and did some work. And I've seen dialogues that are 4 or 5 pages, literally pages long. Okay? Up to you on what you're actually going through and doing. I've had students that go through an outline on their own, type up outlines of the textbook, kind of to review and study the material. That's proof that you've been studying and doing the material. You can just attach that, I'll read through it, yeah, you've been working on it. Okay? That's the sole intent of the dialogue, is to encourage you to be studying the material every week and then just some way to prove that you've been doing it. Okay? Questions about the dialogue? Okay. Subject line is really important. There's no spaces in it. D for dialogue. FA, fall, 1-4, because it is 2014, and then chem236. There are no spaces in it. The reason why I've got this set up is I've got Gmail automatically filtered, or a filter set up that as soon as it sees that subject line, pulls it, and I don't have to look at it. That's not to say I don't look at these, so you can't just send me random BS email, haha, you aren't reading these. I do go back and read them, but I don't want to have to read them every week right in front of me every single day if something else I haven't done. Okay? So I'll go through probably once a week, I would say, for the first couple weeks, and then it turns into once every 2 or 3 weeks, just kind of reviewing them. So if you do send in one of those, haha, you aren't reading them, I'll give you a warning. Okay? That doesn't count as one of your dialogues. And then if you get a second warning, then you lose your opportunity to get the extra credit. Okay? So just send in legitimate dialogues and it's not a problem. You always have to come up with some stupid stick instead of a carrot. Okay? Thought there was something else within that, but maybe not. Questions about the dialogue? Questions about the exams? Okay. Go ahead and move forward. Yes?
So we have 3 exams throughout the class, the whole session, plus 1 final exam?
Yes, just like last semester. So there's 3, they aren't really midterm exams, but 3 exams scattered throughout the semester, which actually are on the schedule already. So you've got one 5th week, was that 9th week, and 13th week. Oh, lucky 13. Tried to break it up within individual sections that I thought made the most sense. And then we'll end with the final exam that covers everything. The final exam is the ACS exam. There is no just second semester ACS exam. It covers the whole year. So you are expected to know some of that material from the first year. I did do a breakdown of it. It's roughly 3/4 second semester and about 1/4 of it is first semester material. Okay, where I would say it's very clearly separated, okay, as those 2 setups. Of course, there is some minor overlap between those. The schedule, I think, is also slightly different than I've seen, at least at other institutions. We're going to start with doing a review of kind of alkenes. Very, very quick review, so those of you that were fans of those fast reviews will be fans of the quick review of alkenes. And then move into the next logical functional group, at least in my opinion, from the alkenes, which is the aromatic ring structures. Okay, your aromatics are benzenes, which is your 6-membered ring with the double bonds. Okay? Why would we not classify that functional group under just alkenes? What's different about that benzene structure? It's drawn up there. We got resonance. Okay? Each of those pi bonds can be shared around the ring, which now changes the nature and characteristics of the pi bond. It's now no longer an alkene. We have to give it a different name because it's a different functional group. It has different chemistry associated with it. Okay? Resonance plays a much larger role in second semester. We'll keep coming back to it. We'll keep practicing it. Keep getting through it. Okay? So we'll look at our aromatics, then we'll hit our exam 1. Exam 1 will primarily cover the aromatics because we aren't talking about alkenes really all that much. There's a little bit of alkene review in there, but for the most part, that's going to be your aromatic chapters. We'll then move into alcohols. Alcohols are a particularly interesting category because they're very useful functionally for pretty much a variety of different activities, which means there's all sorts of different reactions, and their chapter orders tend to jump between all sorts of different sections. So you'll see alcohols showing up in just standard synthesis in substitution reactions, which you've seen already, okay, as a preparation or even reactions of. We'll look at some new reactions of alcohols by getting them activated. Instead of adding acids, what else can we add to actually get them going and working? They show up in redox chapters. And so the way Smith has it organized is you've got your alcohol kind of substitution chapter, and then we have redox chemistry, okay, reduction and oxidation, where you've got some more alcohol reaction showing up in there. To make matters even more interesting, alcohols also show up in the carbonyl chapter when you're jumping up to chapters 20. Okay? So that's, again, kind of why I've balanced this out. So the alcohols will kind of grow through their general chemistry and end our alcohol discussion by looking at carbonyls, which is nice because the next section to study would then be carbonyls. So it kind of transitions at least a little bit as far as their reactivity. Carbonyls, in my opinion, are very, very difficult, okay, or rough to deal with because you've got a whole bunch of different functionality coming through it. When we looked at alkyl halides or alcohols or ethers or alkenes, we're pretty much centered right on the functional group. When we get into carbonyls, we end up seeing chemistry occurring actually away from the functional group, but the functional group is so messed up that it causes the rest of the structure to get messed up as well. Okay, and that's where they become a lot trickier. After our alcohol, or after our carbonyls, we'll move into the carboxylic acids and amines. Most of the carboxylic acid chapters are kind of review. Okay, what might we predict would happen for our carboxylic acids? What are we going to learn about their reactivity? I know it's kind of a trick question. What kind of chemistry would we think of occurs with the functional group of carboxylic acids? Acid-base chemistry. That's primarily what we'll look at with them. We'll see some derivatives of our carboxylic acids, which brings in some other functional groups. But for the most part, we're really kind of centered around just that acid-base chemistry. Okay. Amines. We'll look at a couple interesting reactions with the amines, but the primary reaction we're concerned about with the amines, any guesses there? Name's not going to help you. Carboxylic acids were acids. What do you think amines are? Bases. So the amines will be our counterpart, will act as our bases. Okay? At that point, we'll be done with the semester. Assuming everything goes exactly according to the schedule, which it never will, that last day we can kind of focus on some kind of random interesting things for applications into, say, biochemistry, where you can get carbohydrates, so your sugars, amino acids, looking at that chemistry very, very briefly, so that in theory, when you take biochemistry, even if they don't show you the direct correlation to organic chemistry, you can be like, oh yeah, this guy really didn't know what he's talking about, because that is organic chemistry happening right there. Why are they saying it's not important? Okay. So it is very relevant to biochemistry and biology, at least if you want to understand why. Okay. Then we'll have the final exam, which is already scheduled for Monday. Kind of a rough turnaround there. I will say that more than likely, all of 16th week, I will probably hold extensive office hours, probably steal one of the rooms and just kind of sit and camp out in it. So if you guys have questions, you can always come by and ask questions, okay, to get you prepared and ready for that. Any questions? Excited? I know I am. No questions in general? Concerns? Yeah?
I have a question about the textbook.
Yes.
Is that the green cover, like with a leaf on it?
Yes.
From the book? Okay.
Yeah. You can, if you got the 4th edition, you're fine to use that one too. But I think the 4th edition is $400. You can get the green one, like I said, for $5. It's the same one as we used last semester. That one section that I said wasn't in the textbook, which I'm still not quite sure why it's not in there, is right here. Week 3. I got a lot of work to do. We'll look at the aromatic functional group, some of the chemistry within that chapter. We'll hit the last, or one of the last sections within that chapter, and then the two topics that aren't covered in your textbook, or what I just drew a line through, are the NAS reaction and the Birch reduction reaction. For some reason, I can't find them in your textbook. I don't know why. So I'll build a handout where we'll talk about those in class. So keep your eye out for that. All that information will get posted to Canvas, so you will have access to it. I will try and use the modules as best I can, but more than likely it's just going to make it into the files as a general dump. Maybe you have to sort through folders. Last thing on this slide, I know everybody's favorite, spectroscopy. Everybody remembers spectroscopy, right? What spectroscopy forms do we have? IR, good, everybody remembers that. CNMR, HNMR, mass spec. Okay. Those are going to be our 4 primary factors that we're going to be concerned about. Those are the ones that are really talked about on the ACS exam. When we move into lab, we're actually going to add another one. You won't get tested on it in lecture, but it's just kind of a simple observational thing, which is UV vis spectroscopy. Okay. So using ultraviolet light and visible light. So general review, that link will take you up and review mass spec IR, and your 2 HNMRs, okay, at least as to the level that you need. Throughout the semester with each of these functional groups, as we see more interesting things pop up within spectroscopy, we'll talk about those in a more targeted fashion as well. Okay? So, no questions.
Is spectroscopy in all of those chapters?
Spectroscopy is in every chapter.
It's in every chapter.
Yep. Sapling's usually pretty good about having spectroscopy questions. What you can expect is to see 1 to 2 spectroscopy questions per assignment. Maybe per every 2 assignments, depending on how important I think the reactions are within that individual assignment. And then each exam, you'll probably see 1 to 2 questions on spectroscopy as well, which could be as simple as just what's the characteristics of this type of spectroscopy with this functional group. It could go as far as a complete solve as well. Okay? So, functional groups that everyone in theory saw in first semester Gen Chem. We've got our alkanes, we've got the alkyl halides, and then we've also got the alkenes. Depending on the level of material that you went through before, you might have seen some information on alcohols and maybe a little bit of ethers. For the most part, that's kind of it as far as the functional groups go within first semester. Okay, with our alkenes, what do you guys remember about the reactivity of our alkanes? All right, I may have mispronounced that. With the A, alkanes. How reactive are our alkanes? They aren't very reactive. Okay? So to get them to react, what do we have to do? Well, it's not really elimination. We're going to have to open up Pandora's box and deal with radical reactions, doing single electron transfer reactions to get your alkanes to react. Okay? And in those types of reactions, ultimately all we're trying to do is get the alkane converted into a different functional group. That different functional group is typically an alkyl halide, and in particular, which alkyl halide? The bromide alkyl halides. Why bromide and not, say, chloride, or fluoride, or iodide? Bromide was very selective in your radical substitution reactions. Chloride isn't as selective, but we can actually get that one to work. Why do we not use iodide? Because it's really selective. Iodide isn't used in our radical substitution reactions because it takes forever. Okay? So as we get more selective, it takes longer. But if it takes so long, even if it's really selective, we aren't going to want to do that lab because we want to get out of lab as fast as possible. Why do we not use fluorides? They are so unselective and very, very reactive that they tend to just explode. Okay? And as fun as explosions are in lab, it's usually typically difficult to analyze anything out of that, okay, or isolate anything reasonable. Okay? How might we predict that it had such a low reactivity for our alkanes? Okay? When we move to the alkyl halides are much more reactive. Why are they more reactive? They're polar. When we look at the alkyl halide, or the chloride in this case, if we look at that bond, what's special about that bond? What type of bond is it? So dipole-dipole gives me the type of force, but what type of bond is there between a carbon and a chlorine? It's a polar covalent, meaning it's polar. Well, why is it polar? Why are there partial charges? I agree with that. All back to electronegativity. Chlorine is more electronegative than the carbon, which means it takes the electrons from that bond and they tend to settle on that chlorine. What does that mean happens to the chlorine? It picks up a nice partial negative charge. What charge does the carbon pick up? Partial positive, because that carbon's now lost electron density. Okay. Well, what happens when we get charge? Molecule becomes unhappy and it wants to stabilize somehow or another. Okay, well, let's take it back to the alkanes. What type of bond do we have in the alkanes? In the alkanes with the A, they're sigma bonds. Are they ionic bonds? Are they polar covalent bonds?
No.
What bonds are they?
Non-polar covalent.
They are non-polar covalent. There is no charge building within that structure. If there's no charge, there's no reason to neutralize the charge. Well, if there's no reason to neutralize the charge, what reactions do we have? Nothing. Okay? Because there's no reason for that molecule to interact with any other molecule. If it's not going to interact, we can't possibly run a reaction. Okay? So it can go all the way back to understanding something about electronegativity and a little bit about those bond characteristics, at least for those two functional groups. What happens when we move up to the alkene now? What type of bonds do we have in the alkene? Okay, I like pi bond, and we've got sigma. If we're going to go back to those same classes that we were using for our alkanes and our alkyl halides, we had our ionic, our polar covalent, and our covalent. What type of bond do we have in the alkene? Polar covalent means there's necessarily a separation of charge, a positive and a negative. Which atom is the most electronegative in this structure? Quizzical look is a good time to use it now. Okay. Carbon is technically more electronegative, but by how much? A fraction, which is why the alkane, we said there was no difference. Okay. So when we move to the alkene, we're looking at, again, non-polar covalent bonds. So what might we predict for the reactivity of our alkenes? Low to nothing again. Okay. But what's the big characteristic difference that we've now shifted to when we've moved into the alkenes? We have the pi bond. Well, what's different between a pi bond and a sigma bond? We are looking at a rotation. Pi bonds can't rotate, but why can the pi bonds not rotate? It has to do with where the electrons are located. It has to do with our hybridization. In the sigma bond, okay, we're looking at a direct overlap. So my fingers formed here. Sigma bond forms up. There's our direct overlap of our electrons. Where are those electrons located? Assume my fists are the atoms, the nuclei. Where are those electrons located? Between the two atoms, right? So if I want those electrons to react by bringing in another atom, that other atom has to fight away the two nuclei on the outside. It kind of blocks them. We move to the pi bond. Where are the electrons? Okay, now the electrons are located outside the structure. Okay, where are those electrons located? Now they're accessible. We can bring in another atom to interact with them without having to really encounter the nuclei of those two central atoms. That's going to change the reactivity. And that's ultimately what we end up seeing as far as the chemistry changes when we look at our alkenes as well. Okay? When we move to our alkenes, we're still looking at those London dispersion forces, but they're a little bit stronger. Why are they stronger? The electron cloud is a little bit further away. We can polarize that electron cloud a little bit easier than we could with the alkane. Okay? Melting point, boiling points are a bit questionable to look at, depending on all sorts of structural things. That changes. So that higher melting point, boiling point is kind of questionable. But what happens when we now look at the chemistry associated with the alkene? Well, we're looking at the pi electrons on the alkene. That means our alkene is going to act as an electron source. Okay? What types of reagents act as electron sources? We've got nucleophiles. They want to react with nuclei, hence nucleus-loving, nucleophile. Okay? What charge does a nucleus have? Positive. Okay? So if we want something to react with a positive, what charge does it need to have? Negative. Our alkene can now act as a negative. It can share its electrons with another atom. That other atom, if assuming it's not a hydrogen, okay, and we now have a carbon within our structure acting as a nucleophile, seeking out some electrophilic atom, some positively charged atom. Okay. What if it's hydrogen? We see H plus everywhere. Okay. That's still willing to accept electrons, but that is now such a specific case that we change our definition. Instead of it being a nucleophilic carbon, we refer to it as a BL. I know summer was a long time ago. Bronsted-Lowry base. because it's now sharing those electrons with the hydrogen. All right? This is kind of nice. We've kind of stepped forwards, okay? Went one type of reaction at a time, okay? And since we're hearing some kind of blank faces, because I can hear blank faces, whatever. Let's take a quick moment, step out here, and do a quick review of the types of reactivity that we can see. Okay? So we just talked about a couple of these. If I asked you to classify an individual atom based on its reactivity, what are those types? What are those classes? Okay, I've heard Bronsted-Lowry, which I'm just going to do BL because I don't want to write it out. Bronsted-Lowry what? We have acids and bases. Okay, for it to be a Bronsted-Lowry acid, and I will come back to you. For it to be a Bronsted-Lowry acid, what is it going to do? It's going to donate a proton or donate RH+. Okay, hydrogen ion. What about a Bronsted-Lowry base? It will accept that H+. Okay? So when you look at a reaction, reactants and products, if the only thing that is changed is the location of a single hydrogen ion as a positive charge, and that can be tricky sometimes, we're looking at Bronsted-Lowry acids. Okay? Why is it important to classify that? Because that now allows you to control what reagents might be helpful. Okay? What reagents might be harmful for that reaction to occur. So a quick classification can actually help you out. Teresa, you suggest another class that we can run through? We have Lewis. Lewis what? Wow, that was really creative and original, wasn't it? Lewis acids and bases. What's the definition of our Lewis acid or base? So an electron acceptor is the and the electron donor would be our base. Okay. Is this definition really all that different from our Bronsted-Lowry?
Yes and no.
Good answer. Our Bronsted-Lowry acids do what? Donate H+. Okay. Actually, I like the base definition first. Our Bronsted-Lowry base. What do the Bronsted-Lowry bases do? How do you accept H+? What do you need to have? You need to have electrons, which is typically seen as a negative charge. What does the Lewis base have? Electrons, because it's an electron donor. These definitions are, for all intents and purposes, identical, with one caveat. When we look at the Lewis acids and bases, we're typically referring to those electron donations and exceptions. That was probably not the right phrase there. To anything other than hydrogen. It's technically not true. Our Lewis acid-base definition applies to just the transfer of electrons, period. That transfer of electrons can be between hydrogens. So could we come up with another definition in here that allows us to separate when we're looking at a Lewis acid that's donating to something other than hydrogen? Our last definition is our nucleophiles and electrophiles. So when we have a nucleophile, what's a nucleophile doing? I always have to think through it, actually. So let's break it down. Nucleo is nucleus. Nucleus loving. What charge is a nucleus? Nucleus is positive, so what does our nucleophile need to have if it's going to react with something positive? Negative, or electrons. So our nucleophile is the electron donor. What's our electrophile? An electron acceptor. You'll notice that this definition is identical to our Lewis acids and bases. Okay. So our electrophile, as I think Teresa's walking through too, electro sounds like Electrons. Phile is again our loving. So an electrophile is something that is electron loving. For it to react with electrons, what does it need to have? Positive charge. So it needs to accept those electrons because it loves them so much. Okay? How is this different from our Lewis definition? Okay? The real difference when we're looking at our nucleophiles and electrophiles is these are transfers of electrons to not hydrogen. Okay? So when I go through and look at reactions and look at classes, I tend to avoid the Lewis definition because to me the Lewis definition kind of overarches everything. Okay? Whereas a nucleophile is going to be an electron donor, but it's going to be an electron donor to anything that is not a hydrogen. I can now separate that out and try and find my definitions or find my reagents a little bit easier. Okay? So knowing these classes backwards and forwards will help you. Okay? Worst case, derive them like we just did. Sort of derive them. Questions on that? Please say no, because I just deleted that slide. You can still ask, but... All right, so when we're looking for classes of reactions, that's what I'm asking for. Okay? I'll try and make a slide just like this for every single functional group we come through. Look at the general structure of it, intermolecular forces. Then we'll look at something about its melting points, boiling points sometimes. We'll kind of drift away from those because those properties become less predictable the more complex the functional group becomes. And then we'll look at its reaction classes. Okay, so in this case, for our alkenes, we got that nucleophilic carbon and that basic carbon. Last thing that's on this slide, personally my least favorite thing, are degrees of unsaturation, or what's that other thing that Sapling called it? Anybody remember? I don't really want to remember it either, but it does float in there sometimes. Okay. There's another name for degrees of unsaturation. I don't even quite remember. Not really necessary. When would we use the degrees of unsaturation? As one common time, it's spectroscopy, and it's typically coming from mass spectroscopy. Okay, when we got an idea for a formula, and we want to come up with the degrees of unsaturation, because that can help us whittle down what our functional groups might look like. Okay? Yes, there is this fancy formula, which I can probably take a stab at remembering. You take twice the number of carbons, plus 2, plus the number of nitrogens, minus the number of halogens, minus the number of hydrogens in your formula, and then you divide that by 2. Okay? And if you get 1, that means 1 degree of unsaturation. Well, what's a degree of unsaturation? Pi bond. Hey, look, shows up with our alkenes. What if you got 2? Could be 2 pi bonds, but we have an extra addition that shows up with this. Okay? An alkene is almost, let's draw it slightly differently here. Take our 2 carbons. An alkene kind of looks like cyclic structure. Any kind of ring gives you a degree of unsaturation. Pi bonds are almost a ring. Okay? So when we're looking at our degrees of unsaturation, it's a pi bond or a ring. If you have more than 1 degree of unsaturation, it becomes tricky because now you can get all possible sorts of combinations. You could have 2 rings, you could have 2 pi bonds, you could have a ring and a pi bond. Okay? All those possible permutations come out of it. How important is degrees of unsaturation? Relatively small. Like I said, I don't even have the formula memorized. That's why we got slides. So, alkenes. How can we make our alkenes? Okay, so this can kind of go back to yet another review idea. What types of reactions can make carbon-carbon pi bonds? Take that a step further back. What types of reactions are there? I wouldn't go as far as lots. Holy jeez. We'll address that as a separate issue. Elimination, substitution, what else did you say? Addition. Radicals I'm not a fan of because we get substitution and you get addition. There's another class of reactions. Everybody forgets it. Don't worry. Even the redox, I would say, typically classify into one of those other folders. Okay. Sometimes you'll see them pulled out separately. Sometimes you can just see them folded into something else. The easiest one, your acid-base reactions. Okay. So this again goes back to kind of these underlying ideas. We've got 5 types of reactions here. If we know what these 5 types of reactions are, when we look for a particular functional group, we can say, oh, it's got to be one of these. Okay, where does that functional group best fit in this? So when we look at preparation of alkenes, we want to make a carbon-carbon pi bond, which means if we looked at a reaction, where does the pi bond show up? Left or right side? Of an arrow. Said another way, left being reactant or right being product. Product side. We're trying to make an alkene. That's the end result. I want an alkene there. Which of these reactions results in the formation of an alkene or a pi bond? There is only one. Okay? So if you have an idea of what your functional group is, go all the way back to your electronegativities and kind of come up with classifications. You can then take that back to the potential types of reaction classes, and then we can go into individual reactions and say, okay, I now need to do an elimination. Okay, so what we're trying to do is kind of umbrella and sort of reach further out into further and further subclasses. If we jump immediately to the subclass, we may have missed an important clue that we needed to get through. Okay? So go simple first and work your way into more and more difficulty. Okay? Which is where Isaac was going. With the elimination, I just asked for the reaction. Is there something further than the reaction? What's that something further?
What kind of reaction? Sentence
Is that not writing?
or
That is writing. The mechanism. How did that reaction occur? So for the elimination, what do we end up with?
E1 or E2?
We had E1 and E2. Okay? And just so that we can get all the way to Isaac's suggestion here, which is a valid one. Okay? Is there another mechanism? No, not yet. If we go one step further into this, the E2 elimination actually can break down into what we'll call standard and our Hoffman. Okay. So yeah, the Hoffman is an example of an elimination, but at what level do we encounter that? Okay. It's way steps down into the fine details. At this point, we don't even know what we're reacting with other than we just have an alkene. Okay. So before we get all the way into the details of the mechanism, we want to go all the way back to our reaction type. Okay. What things are we concerned about within an elimination? Well, this next thing is going to kind of cheat, but we end up with our alkene, so we got our pi bond at the product. We need to make that pi bond from somewhere. Okay? What functional groups do we start with for our alkenes? What have we seen so far? Not this semester, last semester. You're looking at our alkyl halides. Okay, the alkanes don't work because we can't form a pi bond immediately from our alkanes. We have to have some kind of leaving group. The leaving group that we looked at in first semester? The halogens, or halides. Okay? So for an elimination reaction to occur, we can go back to our substrate and say, okay, what things need to change? Stick with the simplest functional groups that we have to work with first. Remember, I only talked about 3 so far. Okay? So we're looking at the alkyl halides. We need a leaving group. Something needs to be ripped off of that. Is that the only thing that changes in the course of this reaction? What else changes? Okay? Everybody's favorite. If we look at the actual atom connections and draw in every single bond, as tedious as it may be, what else changed? also lost a hydrogen in the process of this reaction. Okay? Well, if we're losing a hydrogen, more than likely, what charge is it going to come off as?
Positive.
Why would hydrogen come off as positive? Really only has one electron. Okay? So one option I almost always like to do is, if I don't really know, let's draw it out. It comes off as H minus. It comes off with an extra electron. There we go, H minus. Charges are bad, right? So let's evaluate the stability of this charge. How can we stabilize that electron? What does it need? Okay, well, right now it's associated with that hydrogen atom. We could try and bring it near a positive charge. What positive charge does the hydrogen atom bring? It does bring one. The proton in the nucleus brings one positive charge. Try and stabilize that negative. Okay? The balance of that positive and negative is measured by what? Say if we jumped up to bromine, what's the difference between bromine and hydrogen? Electronegativity. The balance of that charge of the positive and negative, we've already gone through and ranked for almost all of our atoms. Okay? At least all the atoms for organic chemistry that we care about. Okay? The more electronegative it is, the more willing it is to hold that charge. Where's hydrogen on that scale of electronegativity? At the bottom. That's not a really good sign. So electronegativity says H minus, horrible, horrible idea. Okay? What else should we evaluate? No, we're still just looking at H minus. We could even bring in the bromine. What else is the difference between hydrogen and bromine? So we looked at that balance of charge, what's in that nucleus. So our electronegativity. We said bromine's really electronegative, hydrogen not so much. So hydrogen, based on electronegativity, doesn't want the electrons. What else? Another big difference between bromine and hydrogen. Bromine is massive. Why is that important? Well, I can take that single electron and I can distribute it over a much larger area. If I've distributed that charge, I've minimized its local effect and it becomes much less reactive because at any given point, the likelihood of finding it there diminishes, and so we decrease the reactivity. So hydrogen, very low electronegativity, doesn't want the charge. And what about its size? It is the smallest element on the periodic table. It cannot stabilize that charge to pretty much any extent. Does that mean H minus never exists?
No.
No? How do we get H minus to exist? There's a lot of extra things that must become involved to help stabilize that charge because the hydrogen, or the hydride technically at that point, cannot stabilize that negative charge well. Okay? So we've got H plus coming off in our reaction. We step all the way back to the reaction again, which means what did that initial structure act as? If it gave up H plus, it was an H plus donor. Let's make it a little bit better than an acid. It gave up H though. If we have hydrogen, it's not nucleophile electrophile. It's an acid, it's a Bronsted-Lowry acid. So if I want this elimination to work, what's a good thing to react that acid with? Base. Okay? Identifying small little bits and pieces, we can start to add things on top of each other to determine what we should react it with. In this case, we want a base. Okay? We could take that further and look at the solvent. Solvent effects are horrible to deal with. I personally hate them. If you got to look at them, you got to look at them. We don't got to look at them, so I'm going to ignore them for the moment. Okay? So we now have these things that we can go through and evaluate. We've got our nucleophile, our base. We've got a leaving group. We have the substrate, where we started from. Okay? Coming up with those small ideas on classifications, we can now start to put it together. Okay? So what two things changed? Leaving group left. Hydrogen was removed. How many things happened? 2. Well, if you got 2 things, does the order matter?
Yes.
Yep. which means when we look at the elimination, how many different ways could the elimination occur? We had 2 mechanisms. Okay? So that's where we had our E1, or our unimolecular elimination, or our E2, our bimolecular elimination. Okay? How did we decide that those 2 things had to happen? It just came back to what things changed. 2 things happened. So we theorized there were technically 3 ways those 2 things could happen. With those 3 ways, we immediately eliminate 1, and we're left with the other 2. How do we decide that those 2 possibilities are valid? Okay, this is always the fun part, in my opinion. Do we find out in the lecture?
No.
No. You have to go into the lab and you run some experiments and see what happens. Okay? Everything that we talk about in the lecture is based on someone's initial hypothesis, what we just went through. Said what things had to happen, what things changed, when did they happen? Well, my theory is all eliminations are unimolecular. I go into the lab, oh crap, I'm wrong. Okay, I changed my theory. They aren't all unimolecular. Some of them can have 2 molecules involved. Then I go back to the lab to see if I'm right. Turns out 90% of the time I'm right. Okay? So realize that when we're talking about these things, it is lab-based. Okay? These experiments someone had to come up with and theorize, come up with that possibility, and then test them. You're then given all of their results and assumed that you look at those results and say, oh, I know how to fix it, the world's problems now. Okay? Which I hope you do. We got enough of them. Okay? So within the unimolecular and the bimolecular, I did a couple things that I thought were kind of important between those. Those of you that have had me before will remember our most important thing for the unimolecular reaction. Stability of the carbocation, which drives everything within unimolecular reactions. Every single possibility, solvent effects, leaving groups, nucleophiles, bases, all comes out of the stable carbocation. You can derive all of those rules. Please feel free to ask about it. When do we end? Sorry, segues. 12:50? What? 1:55. Okay, that makes sense. Okay, all of those can come out of that unimolecular stable carbocation. When we move to the bimolecular, a little bit unhappy with how the bimolecular works out because it doesn't shake out quite the same. You get slightly different dynamics between the elimination and the substitution. Okay? But ultimately, the things that are really coming around that bimolecular has to do with the substrate, how it's substituted, and how we can force that reaction to occur. Okay? So which is going to be the easiest thing to break, easiest bond to break? Think that leaving group or that carbon-hydrogen? Let's highlight those. Here, let's give you colors too. Red and blue. Which bond is easier to break? Said another way, and yes, you're right. What functional group is the carbon to hydrogen? It's the alkane. What was our reactivity for our alkanes? Nothing. What's the reactivity, or what's the functional group for our carbon leaving group? Particularly if we make that leaving group a halide. We've got an alkyl halide. We now actually have a series of reactions possible for that. Which bond is going to be easier to break? The one that actually has reactivity associated with it. So if we're going to try and force this reaction to occur, which bond do I need to be concerned about breaking? Careful. If I want to force this reaction to occur, which bond do I want to break? The hardest bond to break. Because the easy bond is going to do what? Break on its own. So what else do I need for the bimolecular reaction? I need that strong base. I need something to help rip that hydrogen off so that I can actually push the reaction along. And then I'm sure some of you remember too, with our bimolecular elimination, everybody loves this word, the periplanar. Why is that important? That forces the stereochemistry of your products. Also an ACS favorite type of question. I think that showed up twice on the first exam. Okay? So be kind of aware of that. We need to be aware of how these reactions work. So our reactions of alkenes. Okay? So we're now looking at the additions. Okay? So it's a little bit nicer here. Instead of making you fight for what types of reactions you can get, I just gave it to you. Okay? When we're looking at our alkene reactions, we're just going to do addition reaction. Why addition? In substitution, do we start with a pi bond? No. How about elimination? No. Radicals? No. Okay. We only have one option. It has to be the addition reactions. Okay. When we go through and do this addition reaction, we're going to take our pi bond and we're going to react it with something, in this case, XY. Okay? I decided to go through and further accentuate the fact, and we'll love this as this continues to pop up, that we have this pi bond. Okay? So we're looking at p orbitals. And what's somehow happening is we are taking the electrons from our XY bond, and we're now somehow distributing them across those and breaking the pi bond and making some new bonds. Okay? And we end up with some different results in how this ended up occurring. Okay? What's the relationship between those two products? Or could you name the type of addition that happened in each one? We're looking at syn for a syn addition, which is which one, the top or the bottom? Syn is our bottom. Trans is the right idea, though not the quite right word. It's an anti-addition, okay, officially. Okay. So depending on how our mechanism works, we could potentially end up with either of these products, and that is going to be determined based on the reagents that we add. Okay. Can we add some more information into this? Can anybody tell me anything characteristic about X or Y? Maybe charges. If you don't know what the atom is, how could you possibly figure out what the charge was? Any ideas? Let's cheat a little bit. When in doubt, particularly whenever I ask a question, there's a long, long pause. We should go through and draw some special stuff. Special stuff being, come on, you should see those arrows, right? They're a little sloppy, but they aren't that bad. What arrows are those? Resonance. I'm not going to go through with all the primes. Let's say we take the electrons and we put them all on this carbon. That means the other carbon's positive, right? Did I have to put the electrons on that carbon? No. We could have just as easily put them in the other position. Sorry. These structures equal? Why not? What charge? Which charge?
Electrons. The right one. The R groups.
What do R groups have? R groups are typically what atom? Carbon. So really what we're comparing is carbon to hydrogen. Okay? What's the difference between carbon and hydrogen? Electronegativity is relatively equivalent. Size. Why is carbon bigger? What? That's not why it's bigger. It is bigger so it can make more bonds. More, I don't know, someone said it over here. More electrons. What happens when we bring electrons near electrons? They repel. So on that rightmost structure, I've taken that negative charge and I've put it close to two R groups. On the leftmost structure, I took that negative charge and I put it near one R group and one hydrogen. Where is that negative charge going to be more stable? Closer to the hydrogen. Get it away from the electrons. That negative-negative repulsion is bad. Not a good option. That negative, well, I guess I should have, let's do it this way. That's a bad position. Okay, well, what about the positive charge? I mean, come on. There's two of them, right? There's two charges. We should address them both. Okay, Okay, so right now we're saying the negative charge belongs on the left. What about the positive charge? What makes a positive charge less positive? Put it as close as you can to a negative charge, which is ultimately made of electrons. What did our R group bring in? More electrons. Where do we want our positive charge? Closer to the electrons. When we go through and take a look, our leftmost structure again puts that positive charge as close as possible to our electrons. The other positive charge goes towards a hydrogen, which really isn't going to do much to stabilize that positive. So when we look at the resonance structure of our alkene, because it's asymmetrical, meaning we have just one hydrogen on there, we now have kind of a polarity associated with that pi bond, which means the leftmost carbon in our structure up here is most likely negative. The rightmost carbon is positive. Where did the Y atom go? To the positive side, which means that Y atom is more than likely partially negative. Where did the X atom go? Towards the negative, which means that X atom is more than likely partially positive. Interesting. Why stick with this format? When we go through and look at our addition reactions, there's a variety of classifications. I know some of you haven't had me, so you don't know the exact classifications I went through. But we started with alkenes as bases, which means they reacted with acids. What was our positive atom in that case? It was H+. Sure, why not? Let's just erase it all. Our X was H+. And then we added some halide. Okay? Where did our hydrogen atom go? It went to the carbon that already had the most hydrogens, known as, so this is really going to people that haven't had me. What rule is that? It's a Markovnikov addition, because he looked at where the hydrogen went. Okay? Well, that's cool, but that ignores the chemistry. Because if I now go through and put this reagent down, BH4. Remembering, I was pulling at cobwebs. BH4. Anybody remember Markovnikov or anti-Markovnikov? Everyone calls it anti-Markovnikov, and it drives me up the wall. Why? Because he said, well, the hydrogen atom goes to the other position. Kinda. It's not a hydrogen ion anymore. It's H- that was added. Of course it went to the other position because the charges line up. Look at the overall effects of your atoms, not based on the rules, but based on the electronegativity differences and where those charges fall. Does that require extra work on your part? Absolutely, I'm not going to lie. It does. That requires more practice for you to get comfortable looking at each of those positions. What's the alternative? Memorize the crap out of it, which you can do. I can't help you with that, but you can memorize, oh, BH4, anti-Markovnikov, just put the atoms in the other spots. What I want to give you is where these things are coming from and how you can space them together. Okay. We had any minds blown yet? Should I keep going? I think officially I'm done, but we're in this room anyway. Okay, where I'll pick up with Wednesday is looking at just alkene slides. Okay. So I'm not going to go into a lot of detail with these because we pretty much just talked about them. So what I would recommend you go through and do is take a look at each of those reagents. Find the X, find the Y. See how it partners out or pairs out, and you'll find that each of those match that same format with our alkene additions. Okay? You'll notice that some of them have multiple steps. The 1 and 2 ones. Those typically tend to mess with people, and that's where Markovnikov's rules seem to kind of fall away. That's because Markovnikov's rules are ultimately just an observation based on hydrogen. And we saw how good the acid-base definitions were based on hydrogen. Okay, we had to come up with 2 new theories. Okay, so the same thing's happening with Markovnikov. focus on the positive and negative and align those. That's chapter 10. We'll come back to that reaction. Our alkynes, chapter 11, pretty much the same thing as chapter 10. Again, we'll talk about these a little bit. And then chapter 12 is your redox, okay, with your alkenes. Those are your primary classifications within each of those chapters. Ooh, ooh. So we just covered 3 chapters, 1 lecture. Yeah. So